Hey folks, in this video we're going to be talking about permutations and combinations. Now, I should say right off the bat that permutations and combinations are not, strictly speaking, really probability concepts. That said, they come in very useful when we're doing probability. Specifically, as we've defined early on, the basic fundamental equation for probability, number of outcomes we're looking for over total possible outcomes, permutations and combinations come in very useful when it comes to calculating the number of total possible outcomes. So that's why we're looking at them very briefly here. Before we begin, one thing I want to define really quickly is this concept of a factorial. This is something I think a lot of you will be familiar with already, but just in case. A factorial is written as an exclamation point. So we might say n factorial, and that does not mean that we're extra excited about n. It is defined as n times n minus 1 times n minus 2 times n minus 3 until we get all the way down to 1. That is the definition of n factorial, and it's written as this exclamation point. So, for instance, 4 factorial would be 4 times 3 times 2 times 1, and that would be equal to 24. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which would be 720? Maybe 720. I'm doing that off the top of my head. Anyhow, that's how factorials work. One thing I want to point out really quickly is 0 factorial is equal to 1. Just remember that. All right, so let's begin talking about permutations and combinations. Basically, permutations and combinations are the number of ways we can arrange things given different sets of circumstances. With permutations, order matters. The way that we order things matters. So, an example, horse racing. Let's say we go to the track, there's 9 horses in the race. Racehorses usually have really creative names, but I've named them A, B, C, D, E, F, G, H, and I. So not tremendously creative. Let's say I go up to the counter and I place a trifecta bet. A trifecta bet says, out of those 9 horses, I have to pick the first place finisher, the second place finisher, and the third place finisher correctly in order to win my bet. You can imagine that kind of bet pays off hugely if you're correct. Well, what are my actual chances of winning? Let's say I'm just picking names. I have no insider knowledge. I'm not even looking at the odds. I'm just, pointing at I like C, good. That's a letter I really like. I'm just randomly picking. All else being equal, the horse's chances of finishing and the money being equal, how many different ways can this play out? That's what I'm really interested in. How many different ways can I have 3 horses out of 9 finish if I care about the order that they finish? Because remember, my trifecta bet, I'm picking not just the 3 horses that are going to finish in the top 3. I'm picking first place, second place, third place. Order matters in this scenario. So let's extend this example. Let's say I've actually, here's my first place finisher, second place, third place. And I'm going to choose D to finish first. I know I said C earlier, but now I'm just going with D, whatever. D, B, and H. Finishing first, second, and third. That's my pick. If we're defining probability as the number of outcomes we're looking for, or with total possible outcomes, that is one outcome. There's only one outcome that's going to make me a winner. And that is if D finishes first, B finishes second, H finishes third. But how many different ways could this play out? Well, we can do this using compound probability, right? I mean, we can just sort of intuit this thing. We say, okay, well, a number of ways. We can get a first place finisher. There's 9, right? So there's 9 different ways that can happen. But now that we've got a first place horse, how many different ways can we have a second place horse finish? Well, that's 8, and that leaves only 7 horses left running. So we can have 7 third place finishers. You multiply that out and you get 504. That's the kind of common sense way to do it. But this can get a little bit tedious if you're dealing with huge number of possibilities, right? And we've got more than just 3 ways things can happen. This can get pretty complicated if you're dealing with much bigger numbers in terms of not only the number of horses, but also the number of places we're looking to define here. So we can use permutations. And a permutation is the number of ways you can select. Let's call this, a permutation is often written as follows. NPK. And this, we would define this as the number of ways we can select k things from n total things when order matters. And the equation for NPK is this: n factorial over n minus k factorial. I like my exclamation points with a little bit of width. All right, so we could write this. N factorial is just going to be 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. And n minus k, well, okay, what is n minus k? We've said there are three things that were the ways we can select a first place finisher, second place finisher, and a third place finisher. The horse is in the money. There's three. And n is still obviously 9, so now so n minus k is just 6. And yeah, 9 minus 3 is 6. That's what I meant to say. So 6 factorial is going to be 6 times 5 times 4. Ooh, that's not going to be a 4. Close enough. Times 3 times 2 times 1. And now you can just cancel things out. I feel like using a wide range of colors here today. Right? Those parts cancel each other out, and we're left with 9 times 8 times 7 equals 504. The thing is, if you're doing this on a calculator, you could actually just punch in factorials, and so it might actually make the whole thing easier than if you have to write it out like I did up here. So that is permutations for you. Now let's talk about combinations. Combinations are the number of ways you can select a certain number of things out of a larger group if order doesn't matter. So, new scenario here. Let me open up a new page. New scenario here. I go up to the counter, still the same 9 horses, A, B, C, D, E, F, G, H. I think there were H. Now I decide to place a boxed trifecta. You're learning about horse racing betting. I actually had to do some research. I do not know this stuff off the top of my head. I knew the trifecta. I did not know the boxed trifecta. A boxed trifecta says, I'm going to pick the top 3 finishers in any order. So I'm still going to pick, what did I say? D. Well, that's not a D. I think I said D, B, and H. I was getting a little bit ahead of myself there. D, B, and H were the horses I'm picking to finish, but now I don't care, right? If it was my box trifecta, if H ends up winning it and D comes in third, no big deal. I'm still going to win. It's not going to pay as much as a regular trifecta. Or actually, I think it's slightly different with horse racing. I think you actually have to pay more for the box trifecta and then ends up paying the same amount. I think that's how it works. Anyhow, these are just my horses. I still have one way of winning, right? If you think about this in a certain way, I win if the 3 horses I chose finish in the money. They finish 1, 2, 3 in some sort of order. But now, when we talk about the total possible outcomes, it's all the different ways 3 horses out of those 9 could finish in the top 3. That's the total number of outcomes we're looking for. The total number of possible outcomes is all the different ways we can get 3 combinations of 3 horses in the money, meaning the top 3. And so the way to figure that out is, well, we write combinations slightly differently. I used blue last time, I think, so I'm going to keep using blue. We say N, C, R. And this is defined as the number of ways we can pick 3 things out of N things if order does not matter. And order most definitely does not matter in this case. This is all, so in this case, N would be 9 horses. It was written on the other screen, but yeah. So I'm going to redefine it. And R is 3, just like K was 3 when we were doing permutations. And sometimes this is written, for combinations, it's sometimes just written like this. Instead of writing NCR, you just see an N over R inside parentheses. And the equation is slightly different. It's N factorial over R factorial times N minus R factorial. So going back to permutations, K and R are kind of the same, basically the same thing when you're talking about permutations and combinations. Here we had n factorial over n minus k factorial. In combinations, you have the same thing basically. You have n factorial over n minus r factorial, but you also, in the denominator, have r factorial. So this would look like, bear with me, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over, well, r factorial, r is 3 here, right? So it's going to be 3 times 2 times 1, and, I mean, this is, I could put these in parentheses, but it all is going to come out the same. 9 minus 3 factorial is going to be 6 times 5 times 4 times 3 times 2 times 1. And so, again, we can start crossing things out. And now we're left with this. 9 times 8 times 7 divided by 3 times 2 times 1. So that would be, gosh, I forget what 9 times 8 times 7 was. 504, right. Yes, that makes sense. So this would be 504 divided by 6, and that's going to be equal to 84. So if every horse had an equal chance of winning, and I had no information going into my bet, what I would say is I've got one chance of picking the correct combination out of 84 total possible combinations of 3 horses finishing out of 9 when order doesn't matter. That's permutations and combinations for you.